So we're now going to look at how we can use recurrence relations to model simple and compound interest. It's important to make sure that we realize that the rules for writing something in a recurrence form is different to the formulae that we get given for simple and compound interest. So just to remind you, we have two formulae, one for simple interest, which is I equals, so the interest earned equals the principal times the interest rate times the number of periods, or usually the number of years that this is invested or borrowed over. And we have so this one here is for simple interest. We then have a second formula that is for our compound interest, and that one starts with A. And the difference between the A and the I is that A is actually equal to your principal plus your interest earned. So that's the difference there. So let's have a look at it for compound interest. So we have the total amount of your investment, so includes your principal amount, is equal to the principal times 1 plus I to the power of n. So this one is our compound interest formula. So we do use these, and the exam will cover questions that need these. But if the question has this idea of recurrence relation mentioned within it, then don't use these formulae to work out the answer. So we'll have a look at this first question. It says, Jenna deposits $3,500 in a bank account that pays simple interest at a rate of 3.2% each year. And crucially, it says construct a recurrence relation model for this financial situation. So that's why we know not to use those original formulae that I mentioned. I've created a Excel spreadsheet that will show you what is happening here. So simple interest works by you find the rate of the principal. So you find what 3.2% is of $3,500. And in this case, the bank will pay 3.2% of that original $3,500 into the bank account each year. So 3.2% of $3,500 actually works out as $112. So this number here is calculated by doing your principal. So let's write this out. It is found by doing your principal times your interest rate I. And in our case, that means that we have $3,500 times our interest rate, which when we convert it into decimal form is 0.032. And that will actually give you that $112. So when we think about this recurrence form and we go back to what these questions were asking of us, we remember that recurrence means it wants you to state what the link is from the previous to the next term. So every time you move along, you want to say, how are you moving from the one term to the next, and then to the next, and then to the next. So looking at these numbers, we have a look in the amount column. We can see we start with our principal of $3,500. So that's our starting point. So when we think of recurrence forms, remember there are two bits of information we give. We give the starting point and the way that we move from term to term. So in this case, our starting point, A0, is going to be equal to 3,500, which is our principal. And then what we're doing from term to term, well, if we look where we move to next, we move to this value, which is $112 higher. And then from that value to the next value, we move up another $112. So what is happening from term to term is that we are adding $112 every time. So that then means we can write our recurrence relation, AN plus 1, is equal to AN, so the term before, add 112. And our starting point is 3,500. So this would be the recurrence relation for this particular situation. But what would this actually look like if it was just any simple interest question? Well, what will always be the case, so we'll call this the general form. Our general form shows that if you have initial principal amount, that will always equal your A0. So A0 will always equal your principal P. And your relation, your linking of the two from one term to the next is always going to be equal to AN plus, well, the 112 came from working out P times I. So our basic form then is going to be AN plus P times I. And that there is our general form for any simple interest problem. So it doesn't matter what principal or interest rate they give you, if you were to create a recurrence form, it will always be A0 will always equal your principal, and the relation will always be AN plus 1 equals AN plus your principal times its rate of interest. Okay, we're going to have a little look now at a calculator question here. We are told Nikki's investment can be modelled by the following recurrence relation. So we actually get the form this time. So we get A0, which is our principal, is $4,200. And we get told the way you move from term to term is you add 120 to that. So clearly this would have been P times I. We are now being asked to find and determine Nikki's investment after 5 years. So to do this on a calculator, what we're going to do is we need to enter in our A0. So we type in 4,200 and hit the equal sign. Now that's sort of stored as an answer. What we now want to do is tell the calculator we always want to take our previous answer and add 120 to it. So I don't press anything, I just press plus 120, and that now has told me I'm doing my previous answer plus 120. So we need to work out what the investment will be after 5 years. So what I need to do now is say, okay, well that was A0, what is A1, which is the investment after 1 year? Okay, that's 4,320. A2, A3, A4, and A5. So you just press the equals button 5 times to get to this value. So we can see then that our answer is going to be A5 is equal to $4,800. So the investment is worth $4,800 after 5 years. Okay, the next question asks us after how many years will Nikki's investment first exceed $5,000? So go back to our calculator. We've already got to 5 years, so let's see when this ticks over. So the next one will be year 6 and then year 7. Well, clearly year 7 is the first time it jumps over that $5,000. So we can say it takes 7 years for the investment to exceed $5,000. It will be worth $5,040 at this point. And that's how we use recurrence relations to model simple interest.